The quantum internet is an emerging technology that promises to revolutionize the way we communicate, making it faster, more secure, and fundamentally different from today's classical networks. Unlike the conventional internet, which transmits information as bits, ones and zeros, the quantum internet transmits information as qubits, taking advantage of the strange and powerful rules of quantum mechanics. In this video, we will explore what the quantum internet is, how it works, and why it could change the future of communication. At the heart of the quantum internet is quantum entanglement. Entangled particles share a connection that links their states instantaneously, no matter the distance separating them. If one particle is measured, the other's state is immediately determined. This property allows quantum information to be shared in ways that classical signals cannot replicate. Entanglement is what enables the secure transfer of quantum information across a network. The quantum internet is not just about speed, it is about security and reliability. Classical encryption can be broken by powerful computers, but quantum communication can be fundamentally secure thanks to the laws of physics. For example, quantum key distribution, or QKD, uses entangled particles or single photons to share encryption keys. If an eavesdropper tries to intercept the key, the act of measurement changes the quantum state, revealing the intrusion. This creates a level of security that is impossible to achieve with classical methods. Quantum networks rely on quantum repeaters to extend the range of communication. Unlike classical repeaters, which simply amplify signals, quantum repeaters preserve entanglement over long distances. They use a combination of entanglement swapping, error correction, and quantum memory to ensure that qubits can travel hundreds or even thousands of kilometers without losing their delicate quantum properties. Another key aspect of the quantum internet is teleportation of quantum states. Quantum teleportation allows the state of a qubit to be transferred from one location to another without physically moving the particle itself. This process relies on entanglement and classical communication, ensuring that information is transmitted securely and without copying. Teleportation is not science fiction, it has been experimentally demonstrated in laboratories and between satellites and ground stations. The quantum internet will also enable distributed quantum computing. In a distributed system, multiple quantum processors can work together across a network, sharing entanglement and quantum states. This allows larger and more complex problems to be solved than any single quantum computer could handle alone. Essentially, the quantum internet could connect quantum devices into a global computational network. Quantum communication can also improve timekeeping and synchronization. Atomic clocks linked via quantum networks can share timing information with extreme precision. This could improve GPS accuracy, scientific measurements, and synchronization of global networks far beyond what is possible today. Building a quantum internet faces significant challenges. Qubits are extremely fragile and susceptible to noise, making long-distance transmission difficult. Engineers must develop reliable quantum repeaters, error correction techniques, and memory systems that preserve entanglement. Satellite-based networks are already being tested to overcome some of these obstacles, allowing entanglement distribution over thousands of kilometers. China, the European Union, the United States, and other countries are investing heavily in quantum internet research. Experiments have already successfully entangled photons between ground stations and orbiting satellites, demonstrating that global-scale quantum networks are feasible. These milestones show that the quantum internet is moving from theory to practical implementation. In simple terms, the quantum internet is a network where information is transmitted as qubits rather than bits. It uses entanglement, superposition, and teleportation to send data securely, efficiently, and in ways that classical networks cannot match. The promise is not just faster communication, but fundamentally secure and highly integrated global connectivity. The quantum internet also represents a shift in thinking about information. It is not just about sending messages, but about sharing quantum states, linking processors, and creating networks where the laws of physics themselves enforce security and reliability. This opens new possibilities for science, technology, and even society at large. In the future, the quantum internet could underpin secure global communication, link quantum computers for distributed computation, improve measurement and navigation, and enable entirely new applications we cannot yet imagine. It is a technology that builds directly on the counterintuitive principles of quantum mechanics, turning the strange rules of the microscopic world into practical tools for the macroscopic one. Understanding the quantum internet today gives insight into the next generation of communication. It is a bridge between quantum physics and technology, offering unprecedented opportunities to rethink how information travels, how it is protected, and how it can be processed. The quantum internet is not just a dream, it is rapidly becoming the next frontier of the digital world.